Hello everybody, Mystery Scholar here with a segment I like to call Did You Know? Today I'd like to share with you an amazing connection I found between lions and the sun. I had always wondered why we have an association between lions and the sun throughout many cultures, and throughout an investigation of sound I found this amazing connection. The first thing I'd like to draw your attention to is the average frequency of a male African lion's roar. With a little research, I found that between 180 and 190 hertz, we have the average frequency range for this roar, with a peak range at about 186 hertz. So 186 hertz, we have the peak range for a male African lion's roar. So we'll set that aside and now turn to the sun. With a little solar anatomy, we need to figure out what could be thought of as the roar of the sun. And I kind of figured it has to do with the photosphere. So the photosphere is a very thin layer of the sun where the light of the sun is actually generated. Beneath this layer, the sun is actually completely black, dark. There is no light generated within the photosphere. It is only in the photosphere itself. So sub-photosphere, there is no light. And so if we look at the solar anatomy, we see that the solar radius is about 432,000 miles. That's the radius, the distance between the center to the outer edge of the sun. The photosphere is only about 300 miles thick. This is about 0.07% of the original thickness. So the photosphere is only 0.07% of the thickness of the sun, a very, very thin layer. Beneath that, the sun is completely black. So we have this distance between the edge of the sun down to the bottom layer of the photosphere being about 300 miles. So our frequency formula requires two things. We need a velocity and a wavelength. And so I'm choosing the velocity of sound through air because we see the sun through the atmosphere, and so the light that's generated, the sound, actually passes through the atmosphere of the Earth. And so we have the velocity of sound through air at an average of 1,125 feet per second. That's the velocity of the sound that I'll use. So 1,125 feet per second goes in the numerator of this equation. Now the denominator is the wavelength. I'm considering the distance of the photosphere, or the thickness of the photosphere, to be my wavelength. So one fundamental wave fits within the photosphere, and so that wavelength is 300 miles. However, this unit of miles does not correspond to the unit that I have for my velocity. So I need to change them and make sure they're in the same units, and I'll go ahead and keep feet. So 300 miles is actually 300 miles times 5,280 feet in 1 mile. So using this conversion, I'm left with feet as units, and this result gives me a wavelength of 1,584,000 feet. So that's my wavelength for the photosphere. And again, I'm considering the thickness of the photosphere to be my wavelength. So 1,584 feet, so 1,584,000 feet is my wavelength. And so now I can go ahead and do this calculation to calculate the frequency of the photosphere. So 1,125 divided by 1,584,000 yields 0.0007, let me get this correct, 0.007102, and then 27 repeats. So that's an interesting decimal that we have 0.007102 and then 272727 repeating. And again, that's the frequency or hertz value for the photosphere. Now, to hear this means that we have this many cycles per 1 second. In other words, we would need about 1,000 cycles, or 1,000 seconds to hear 1 cycle. So that's a bit too low of a frequency to hear. So if we actually increase this frequency to an audible level, then we can associate that with some sort of sound that we have. And so to increase this to an audible level, we just multiply by 2. Simply multiplying a frequency by 2 just shifts it to the next octave range, keeping the same energy structure just increasing the energy. So taking this value, so our frequency is 0.000710227 repeating hertz. And I would just take this and multiply by 2 until I get to an appropriate level of audible range. So we're considering an audible range of around 1 to 200 hertz. So we can multiply this by 2 until we get to a frequency that's between 1 to 200 hertz. And since I've done this before, if we multiply by 2 18 times, in other words, multiply by 2 to the 18th power, or find the 18th octave of this frequency, we get 186.18 repeating hertz. So that's not repeating hertz, that's a repeating decimal. And so again, we've got this frequency value is actually too low to hear. And so if we boost it to an appropriate octave level of audible range, we find that the sun, or the photosphere of the sun, has a resonant frequency at 186.18 hertz. Drawing your attention right back to the lion, I have it right here above. So the male African lion has a frequency of about 186 hertz as its average peak frequency for the vocalization. And here we have the vocalization, or the sun's frequency in terms of sound, resonates at 186 hertz. So I find that to be a truly remarkable, perhaps coincidental connection. But I truly believe that it's beyond coincidence, that it's possible that the ancients knew this connection, or perhaps could perceive this connection via some understanding of cymatics. And so that is the lion and the sun connection, and perhaps that is why we associate lions with the sun.
Good.